phi, the S1 with the S2, then you get the M. Again, well, and I'm not going to state this version of Maske's theorem, but what this is very similar to that one. So what you have to do is an HNN extension of this one, and the similar kind of theorem holds for this case, even if the S is non-separating. Okay, because this picture is easier to understand, let me stick to this separating case. Okay. So, to show the uniformization theorem, to complete the proof of the uniformization theorem by proving the last stage of the induction, you have to show that, so we assume that M1 and M2 admit geometrically finite structure. And what you have to show is you can just adjust them so that the corresponding Kleinian groups, here, so the corresponding surface, Kleinian surface groups are the same. Okay. So what Thurston used to show this is the case is what is called skinning map. So, well, because M1 or M2 has a geometrically finite hyperbolic structure, then if you restrict that structure to the surface S, then what you get is quasi-Fuchsian. Well, this needs a proof, but any surface group, any Kleinian surface group containing a geometrically finite Kleinian group, which is not the surface bundle over S1, must be quasi-Fuchsian, actually. So, so you get some quasi-Fuchsian group here. And down here, you also have a quasi-Fuchsian. So from M2, you get another quasi-Fuchsian. So we'd like to make them the same. Okay. So now, we know, so I explained the quasi-Fuchsian space of the for yesterday, and there actually, so that's what Alphonse Beer showed, but there's general theory of the deformation of geometrically finite structure used in the quasi-conformal deformation. So the deformation space of geometrically finite structures. So suppose G1 is the geometrically finite. Then there is a map from the quotient of the domain of discontinuity to the space of quasi-conformal deformation of G. So the special case when G is Fuchsian was dealt with yesterday. So in general, there is Alphonse Beer's Maskit, Kura, Marden. the theorem saying that there is some ramified covering of the space of conformal deformation by the Riemann surface corresponding to the domain of discontinuity. Okay. So, well, because this is the final stage of the proof that the M is closed. And so the M1 has only boundary S. So M2 is the same. So the M2, the boundary of M2 is just S. So this should be S. Okay. And the same holds for oh, this should be G1. The same holds for G2. Okay. So what you have to show is by deforming the structure by quasi-conformal maps, you can reach the situation where these two quasi-Fuchsian groups are the same. Okay. But the point is you have, so the dimension of the deformation is just the same as the Teichmüller space here, and this is also Teichmüller space. But the condition you have to have has the double of that dimension. So in general, it might be difficult. But the Thurston proved that this can be done. So what he did is something like this. So you first, so suppose you have some structure here, M, okay. Then you take the covering of the M by the fundamental, corresponding to the fundamental group of S. Then you get a quasi-Fuchsian group. So, and the Riemann surface, so you have two domains of discontinuity. The one of them is just a lift of the domain of discontinuity here. So you have a structure M down here. But you have another structure here, which is hidden in M1. So this should be the QM. Okay. Now, because this is the point in the Teichmüller space, you can put that QM here. Okay. And you get some geometrically finite structure on M2. Okay. So you put QM here. Now, so because this is the geometrically finite, then if you take a covering associated to the Parman numbers, you get another structure down here. So that should Rm. Okay. So starting from M, you get Qm, and well, just identify this structure with that. You get Qm here, and then another structure Rm comes. Okay. So because the quasi-Fuchsian group, the space of quasi-Fuchsian groups is parameterized by these two structures. So to guarantee that these two are the same, what you have to show is the M and Rm coincide. Okay? The condition is we need to find M such that M is Rm. Okay. So we can regard this problem of the finding of a fixed point. So start from some M, you get some Rm by this construction. And what you have to show that is you can find M such that Rm is equal to M. So what you have to show is this map R has a fixed point in the Taiheimura space. Okay. So actually now there is a direct proof of this fact showing that the R is just using a technique of the complex analysis, which was done by McMahon. But Thurston's original proof doesn't use the complex analysis at all. So he showed that, so he tried to iterate this map. And if that converges to some point in a Taiheimura space, then that must be a fixed point, right? But in general, you cannot guarantee that this converges inside the Taiheimura space. So that it might diverge. Okay. So first to analyze what happens if it diverges. And that's the place where he considered the general theory of Kleinian groups. So suppose, okay, M diverges. Okay. And well, so again, we to sketch the proof of this well, to show how he argued, well, we need another assumption that suppose M1 is acylindrical. That means M1 does not contain an incompressible annulus. The proof of this case is dealt with in the first part of his the Thurston's series of papers. And the proof in general, well, if you allow the incompressible annulus to exist in M, then the proof is, well, a kind of proof appears in the third part of the Thurston's series. Okay. And so suppose M1 does not contain, well, why we need such assumption? Because so the QC of G1 lies in a larger space, AH of G1, which I defined yesterday. It is a deformation space, the entire deformation space of it. So that is a space of the faithful discrete representations of G1 into PSL2C, modeled out by the conjugation. Okay. And if M1 is acylindrical, then AH G1 is compact. So in general, the deformation space of the Kleinian group is not compact. For instance, if G1 is Fuchsian group, it's not compact. The Taiheimura space lies there, and it has a, so in that direction, the space is non-compact. Okay. So if we know that this is compact, then even if the RKM diverges in TS, the Taiheimura space, well, if you map it to QC of G1 and regard it as a point in AH of G1, then it must converge to some point. Well, if you take a subsequence, it must converge to some point of AH of G1. And what Thurston showed is if RKM or RKM, what's the name of the map? So I haven't defined the name of the map, but that should be QC. So if QC of RKM converges to a point in AHG1 minus QCG1, so that is if that converges to a boundary point of the deformation space, then you get the contradiction. Actually, he showed that then the limit group, so instead of QC, you consider the covering associated to, in the limit group, subgroup corresponding to S cannot be quasi-Fuchsian. Actually, he showed that it is either something called a regular B group or geometrically infinite group, and both of which case cannot happen actually. And this is contradiction. So here, contradiction. Here he uses, so here we need use some theory of advanced theory of the Kleinian groups. Actually, if you have some hyperbolic structure on MM which is not geometrically finite, and he could show that the limit group cannot be, so if the limit group, so the subgroup corresponding to the limit group is geometrically infinite, for instance, then he showed that there is something called the covering theorem holds, and it cannot be a subgroup of such a bigger Kleinian group, and something like that. So this part is also difficult, but modulo this part, the general line of the argument is like this. Okay. So that's what Thurston. I have no time to continue. So maybe the time is up. So I should stop here. So so what I wanted to show is how Thurston proved his uniformization theorem and how Kleinian groups are important in his proof. Okay, that's all.